give us secant x as a derivative, and what function would give us tangent x as a derivative? Anyone want to tackle this? You know, you asked me what the derivative of secant is. I don't have it memorized. What I can tell you is that secant is cosine x, and tangent is sine x divided by cosine x, and that may help me. It may not, I don't know. It may help, it may not help. That would be the same as cosine x to the negative 2 power and sine x. Well, do we know what sine x is? Can we figure that one out? So that one we know at least would be, did you say cosine? How about negative cosine? Because the derivative of cosine is negative sine. Okay, so negative cosine. And then how we tackle the other here, I'll put the plus c on there. We'd have to go in, and then, you know, that's a composite answer here. Let's see, if I do my rule, it would be cosine x to the negative 2 plus 1 divided by negative 1. Well, if we, okay, so to create the function, we'd have to add 1. And then that would give us negative cosine to the negative 1. Would that do it? If I take the derivative of this, it doesn't quite make it, does it? Because if I take the derivative of this, yes, I would get cosine to the negative 2, cosine x to the negative 2. I guess that's what I need, isn't it? So this would have to be negative cosine x to the negative cosine x to the negative 1. Help me out here. Am I right? Okay. So I end up with y is equal to, what isn't what my answer is supposed to be? I'm looking at 1, aren't I? I need secant. Yeah. I need secant in there. How am I? Secant is 1 divided by cosine. I was hoping. Yeah, Becca, what do you see? So say it again.
Like, isn't that just a rule that secant x tangent x is always greater than
Yes. Yes. Okay. So, and that, yeah, if you got that, I don't have that memorized, obviously. Okay, so if we have it memorized, we got it. Okay, well, that was just one of those that kind of a challenge in there. The other one that I want to give you is this one. And the oops, not use red here. The derivative is 4 divided by x. Now, you could say, well, that's the same as x to the negative 1. I'll just apply the same thing. Tell me what happens. Yeah, I end up by dividing by 0, which I can't do. So there's got to be another way around this. So then we can say, well, that's true, but it's also 4 times 1 divided by x. And that's another one of those derivatives that you may or may not remember. Yeah, the natural log. So it'd be 4 times the natural log of x plus c. Okay. Well, what we're doing in Chapter 5 is exactly this. we are going to be given the derivatives. And we have to come up with the functions. Now, in order to do that, we need to have, of course, better notation, because in order to communicate this to you, I have to write some words. I don't have the words written out. I spoke them to you. You know, find the function that yields this derivative. We need a notation for that. We need a symbol for that. And so the symbol that is used is this elongated S. Leibniz and Newton kind of had an argument, so they compromised and used the long elongated S on it. So if I had this, for instance, now the only thing that's missing in this notation is if I have more than one variable, I need to be able to communicate which of the variables is truly the input variable of my function and which ones would just be considered as constants. What should we do? What do you think we could use to indicate that the x is our variable, our input variable? Yeah, we'll use that differential x that we have in our notation. So if we use this notation, this is called the antiderivative. The non-derivative. It says find the function that yields, and this portion of it is what? This is a derivative, yes. This is a derivative, and we are trying to find the function that would yield this derivative. And so our answer would be 4 natural log of x plus c. Okay, this is what we're about. Now, it gets a little more complicated in all of this, because then we're going to impose some limits, some boundaries, and we're going to say, I want to find this, but I need to make sure that I understand that my input variable is only going to range from 0 to 5 or pi to 3 pi divided by 2 or whatever. And so that becomes a whole nother dimension on this. But basically what we're doing is playing Jeopardy. I'm giving you, the book is giving you all of the derivatives. You've got to come up with the function that yields it. So when we look at this notation, you've got to remember, this is our derivative. This indicates the input variable. The input variable with the differential x, just like it was in our work here. Now, if we want to check answers, we can go to our Inspires, and if you go into calculus, you're on the calculator page, and do an integral, we have then the option of putting in these what we call lower and upper bounds. But we can bypass that and just put in our fraction. I'm not sure what answer we're going to get, so we're going to try it here. And we've got the natural log of x. Now, do I have to use x? No. If I'm not going to graph it, I don't have to use it. Use x. I could use anything, and we come up with this answer. Now, it doesn't know what to do. Whoops, I guess did exactly what I wanted to, didn't I? I just gave it the wrong thing. So let me back up here. I just wanted x, didn't I? There we go. There we go. Now, why would we have the absolute value on this? I didn't put it in our work, but the Inspires reminding me that we should have. Well, can you take the natural log of a negative quantity? What if I had the natural log of -2? I'll put a little space holder there. This is my exponent. My exponent on what? What's the base of my exponent? E. So e to what power gives me -2? Is it possible? No. And that's why it has the absolute value in there, because it's impossible to take the take a log, whether it's natural or any other, to a negative quantity. Okay, well that's just the introduction to this piece. Let's go now to the notes, and again, I will make these available to you. We're talking antiderivatives and indefinite integration. What we have, and remember, in math, capital letters and small case letters do not mean the same thing. So capital F is the antiderivative of a function on an interval. In other words, if I take the derivative of cap F, I would get the derivative. So we have to, in this notation here, the derivative of cap F is this, so this is a derivative that we're talking about here. F of x is the function. The antiderivative. It's not the derivative, it's the antiderivative. So it's the function, in other words. So if f of x, cap f of x is the function, then the derivative of cap f is small case f of x, and it would be then our derivative. If we have a function with a constant, then this is just noting that we would have the same thing, you know, the derivative of this function would just be this derivative. So again, in our work here, the first piece of this I think can be a little confusing because we combine the capital F and small case f. But I'll keep reminding you by drawing it here and writing it, this is a derivative. Okay. And again, this piece tells us the input variable. Okay, so just a little bit of notation, and we'll come back to that. What's the antiderivative notation? Well, it would be the integral, indefinite integral of. Now, why would it be important to put parentheses there? What if I just wrote this? Instead of the whole quantity, yeah. But it would also be incorrect if you put that here because this is incomplete. What's missing down here? As well as up here. Yeah, the differential x, dx. So if I wanted to have both of those, I'd have to include a dx here, and then it truly would be like that. Okay, so make sure you put parentheses in. Otherwise, it will be counted as incorrect because it's not correct. Okay, representation of antiderivatives. Here's this capital F again. Cap F refers to the function, okay, is an antiderivative of small case f. I'll put that in green on this one. Which one of these is the derivative? Cap F or small case f? Small case f. So this is the derivative, and this is the function. Okay, on an interval, then G is an antiderivative. So we have that F is an antiderivative. Now we're saying G is an antiderivative also. So we have two things. In other words, we have two functions that have the same derivative. That's what this is saying. If F is a function whose derivative is small case f, and then G is an antiderivative of f also, okay? That's true if and only if the second one is equal to the first one. There's that constant, okay? There's that constant. You know, if I'm looking at cap f of x to be 2x, let me write this correctly, to be x squared plus 3x, then g of x could be x squared plus 3x plus 4. They both have a derivative of 2x plus 3. I could have h of x, and I could have x squared plus 3x minus pi, and that again, all of those would have the same derivative. That's what this theorem is saying. Okay, nothing much except that. Now, again, I'm not going to give you time to write every word down because it will be coming. Name the steps in the process. We've already done that. Okay, and the process To determine the derivative, we multiply the